For centuries, physicists lived in a comfortable world, a world where the laws of nature seemed clear and unchanging. It was a world built on the solid foundations laid by Isaac Newton, whose theories provided a framework for understanding the cosmos. Newton's laws of motion and gravity could explain the motion of planets, predicting their orbits with remarkable accuracy. They could predict the trajectory of cannonballs, allowing for precise calculations in warfare and engineering. They even explained the ocean's tides, linking the movement of the seas to the gravitational pull of the moon. The universe, it seemed, was a giant clockwork mechanism, everything ticking along predictably, like the gears of a well-made watch. Then came the late 19th and early 20th centuries, a time of great change and discovery. Scientists began to probe the universe in new ways using advanced instruments and innovative techniques. They looked at the very small, the world of atoms and light, uncovering mysteries that Newton could never have imagined. What they found shook the foundations of physics, revealing a universe far more complex and unpredictable than previously thought. The neat, predictable world of Newton was about to be turned upside down, as new theories emerged to challenge the old. Get ready for a wild ride, as we explore the revolutionary ideas that reshaped our understanding of the universe. One of the first cracks in the classical edifice appeared in the study of light, a fundamental aspect of physics that had puzzled scientists for centuries. Physicists knew that hot objects emit light, a phenomenon observable in everyday life. Think of a glowing piece of metal, like the kind you might see in a blacksmith's forge. Classical physics predicted that the intensity of this light should increase indefinitely as the wavelength got shorter, leading to a paradox. This paradox suggested that a hot object should emit an infinite amount of ultraviolet light, which was clearly not the case. This discrepancy was so significant that it was dubbed the ultraviolet catastrophe, highlighting the failure of classical theories. In 1900, Max Planck, a German physicist, came up with a revolutionary solution that would change the course of physics. He proposed that light energy could only be emitted or absorbed in discrete packets or quanta rather than in a continuous flow. The energy of each quantum was proportional to its frequency, a concept that was both radical and groundbreaking. This was a radical idea that challenged the very foundations of classical physics. It implied that energy was not continuous but came in tiny, indivisible units, a notion that would eventually lead to the development of quantum mechanics. Planck's idea was initially met with skepticism. Even Planck himself wasn't entirely convinced at first, but then came Albert Einstein in 1905, changing everything. Einstein used Planck's quantum hypothesis to explain the photoelectric effect brilliantly. This is the phenomenon where light shining on a metal surface can eject electrons. Classical physics couldn't explain why this effect depended on the frequency of light, not just its intensity. Einstein showed that light could behave as if it were made up of particles, later called photons. Each photon carried a quantum of energy, just as Planck had originally proposed. This was a huge deal in the scientific community. Light, which everyone thought was a wave, could also act like a particle. The wave-particle duality of light was born, revolutionizing physics. Section 4, Quantum Mechanics, A New Worldview. These discoveries opened the floodgates to a realm of possibilities that were previously unimaginable. In the years that followed, a whole new theory of physics emerged, quantum mechanics, which revolutionized our understanding of the universe. Niels Bohr used quantum ideas to explain the structure of the atom, providing a groundbreaking model. He proposed that electrons could only occupy specific energy levels within an atom, a concept that was both radical and transformative. When an electron jumped between levels, it emitted or absorbed a photon with energy equal to the difference between the levels, a process that was key to understanding atomic behavior. Then came Werner Heisenberg, Erwin Schrödinger and others, who expanded on Bohr's ideas. They developed a more complete mathematical framework for quantum mechanics which provided deeper insights into the nature of reality. This framework was strange and counterintuitive, challenging our traditional notions of how the world works. It abandoned the deterministic worldview of classical physics, which had dominated scientific thought for centuries. In the quantum world, particles didn't follow well-defined paths but rather existed in a state of probabilities. Instead, their behavior was governed by probabilities and uncertainties, a concept that continues to intrigue and challenge scientists to this day. Section 5. Join the quantum conversation. The development of quantum mechanics was a revolution in physics. It completely changed our understanding of the universe at its most fundamental level. From the transistors in your smartphone to the lasers in your Blu-ray player, quantum mechanics is the foundation for countless technologies we rely on today. But more than that, quantum mechanics forces us to rethink our place in the universe. It tells us that the universe is not a cold, predictable machine but a place of constant flux and uncertainty. So what do you think? Does quantum mechanics blow your mind? Share your thoughts and let's keep the conversation going.